I'm going to work through an example of the force of gravity, in a very particular case, so the force of gravity on you, which we ordinarily would just call your weight. So your weight, which we'll call W, is your mass in kilograms times the acceleration due to gravity, which is little g, and that also has to be the force of gravity pulling on you from Newton's law of universal gravitation. So it would be capital G, mass of the Earth, times your mass, and you're on top of the surface of the Earth, so you're the radius of the Earth away from the center. So the 1 over r squared is going to be Earth's radius squared. Some values. Big G is 6.674 times 10 to the minus 11, and we use that as Newton meter squared per kilogram squared. Mass of the Earth, 5.9722 times 10 to the 24th in kilograms. And Earth's radius on average, 6.3781 times 10 to the 6th in meters. So 6,378 kilometers on average. And obviously, some places it's higher and some places it's lower. All right, so let's get back to our equation for the weight. Weight is going to be your mass times little g, which will be big G, mass of the Earth, times your mass over the radius of the Earth squared. And if you look at that for a second, it must be the case that little g here, the acceleration due to Earth's gravity, is given by that combination, universal constant of gravitation, mass of the Earth over radius of the Earth squared. So let's go ahead and calculate that. Little g, universal constant of gravitation, Earth's mass, divided by Earth's radius squared. We're going to have 6.674 times 10 to the minus 11 Newton meter squared per kilogram squared. Mass of the Earth, 5.9722 times 10 to the 24th kilograms. And the radius of the Earth, 6.3781 times 10 to the 6th meters squared. Let's check our units as we're going through here. So I have meters squared up top. It's going to cancel out with that meters when we square it. And then 1 power of kilograms there. Cancels out kilograms. So we're going to get an answer for a little g that is newtons per kilogram, which is also meters per second squared. So that is correct. All right, and you put that in your calculator, you're going to get little g, 9.7980 newtons per kilogram. And now we want to think just a second about significant figures. Because even to this day, universal constant of gravitation is not terribly well known. That has 4 significant figures. Value I use for the mass of the Earth is 5 significant digits. Raised to the Earth is 1, 2, 3, 4, 5. So this answer for little g can't be more precise than having 4 significant digits. So what I should write out as my answer is that little g is 9.798 newtons per kilogram. And later in the semester, you'll use a pendulum to very carefully measure the acceleration due to gravity here at Earth's surface, but just for the value local to Kokomo. In some places you can find deviations. For example, when I was in Boulder, you had mountains yanking on your pendulum, so that would change things a bit. But you can measure for yourself if the local acceleration due to gravity is 9.798 or 9.797 or so forth. So this is the value that follows from the average value of Earth's radius and not taking into account any of the inhomogeneities underneath us. So there you go. Big lesson out of this. Please never, ever, ever mistake universal constant of gravitation, capital G, for little g, where little g is the local acceleration due to gravity. Okay. Capitalization matters. Don't make that mistake.